All right, now we want to look at moments for two or more variables. And it's pretty much the same idea. If we want the expected value of, say, g of x and y, some function of x and y for a relative to a two variable probability distribution, then again, if we look at the discrete, that's just the sum over I, sum over j of g of xi yj times our f of xi yj. And of course, we would just do an integral if we were using continuous variable. They have some notations. They have alpha and m. That's just the expected value of x to the n, y to the m. And then they use a mu here. I don't like the fact they use a mu for these, but unfortunately, we're stuck with it. And so this is x minus mx, the mean of x, to the n times y minus the mean of y to the m. Whoops. There we go. Okay, and so let's see. They just they have some observations at the end here. So they mention that. So for instance, alpha 1, 0, which is e of x, expected value of x. And so, because alpha 1, 0 would be, by definition, this thing with n equal 1 and m equals 0. And we can see that, that it really does work that way. If we use continuous, we would have x and then f of xy, say dy dx. But now, just move that x out of there, and you have the integral from minus infinity to infinity of f of x y dy dx. But now, this part is just our definition of the marginal distribution fx of x and dx. And so, that's e to the x. And let's see. So they point out that sigma squared x, well, that's in their notation, that's alpha 2, 0 minus mx squared. Well, alpha 2, 0, this is e of x squared minus mx squared. And similarly, sigma y squared is alpha 0, 2 minus my squared. And so this would be e of y squared minus my squared. But of course, since mx is e of x, and my is e of y, you could also, write that as alpha 1, 0 squared, and you could write this one as alpha 0, 1 squared. Okay, so we have that for the variance of x and the variance of y, even in a joint distribution. Okay, so we'll stop that one there.